Actually, Jean-Yves told me to plug this in. I don't know what that does. Maybe I'll do that. It does actually change something there. What? Oh, maybe that's a microphone. Yeah. Okay. Thanks. Okay. Sorry, that reminds me of, I saw a talk by a theoretical physicist, and at some point he had to do a little demonstration, and he paused and he said, "I'm not just a theoretical physicist, I'm a very theoretical physicist." Oh, that was funny. Okay, so we were we had just derived Bernoulli's equation, and oh, great. We have a participant, welcome. And I should, oops, open the chat just so they know we can type questions there. And I didn't mean to click on there. Okay, so we derived Bernoulli's equation, and now, which was like an energy equation, or yeah, right, an energy equation, because we multiplied by the velocity in order to convert the momentum equation into a I call it energy, but it's the terms are actually power, right? Yeah, it's the rate of change of energy equation, or an equation talking about or determining the time evolution of the energy. The Euler equation is based on the momentum equation, and we leave it in momentum form, but we just go back to the control volume version, as you'll see here. So, so we return to that general momentum equation, which is not the Navier-Stokes equation, but it's the one written here. It's not the Navier-Stokes because I have the stress tensor. It's Newton's second law applied to a continuous medium, a fluid, but I haven't committed myself on the form of the viscosity, so I just left the stress tensor in its general form here. And then I multiply by the density so that it appears in the numerator in all terms except the stress tensor. And then I'm going to use the continuity equation, which was also from lecture 3. Remember, that's the one that has a funny name, but it actually expresses the conservation of mass for a continuous fluid, continuous medium, such as a fluid. And but that one I multiply by the velocity. So I'm multiplying by u. It is important to pay attention to the indices. So I'm multiplying by the ui, not uj, right? The j index here is the same as the one there, and then I multiply by I. So there's a sum over j, and then all that sum is multiplied by ui. And then we add the two equations. And we get this equation. There's just 0 on the right-hand side of 23. So it doesn't add anything, but on the left-hand side, we have this extra, see, I guess, here I have rho d or partial t of ui, and then here I'm going to have ui partial rho partial t. And so when you combine those, the motivation, I guess, is to be able to combine those two terms, like this term and the first two terms here, they're going to combine to give you this one single term here. So that's just a result of differential calculus that allows you to join those two terms together. And similarly, with the third and fourth term, you can join those two together and write them like this. So that should be familiar from differential calculus. And so this is like our general momentum equation. This is valid for a general continuous medium, such as a fluid. So we don't, we're more general than Newtonian fluids here. And it does not have to be incompressible either, right? It could be a compressible fluid. So this would apply at high Mach number in the atmosphere. But let's start introducing some restrictions to simplify this. Let's apply it to the case of a steady flow. And so in other words, it's stationary in time. So the Eulerian time derivatives vanish. So this term no longer appears, but I still have the advective term. And that's all I've managed to do with that stationary time approximation. And now we consider this applied to a control volume V, an imaginary surface that we cut in the fluid. It's important that that control volume be inertial. So I suppose it could move with respect to our reference frame, but it would have to move at a constant uniform velocity. But the simplest thing is that it's not moving, but it's just an imaginary, or it could be an imaginary surface, just to allow us to talk about a certain volume V of the fluid. But it could happen to. Sometimes we often line up those imaginary walls with the real walls of the vessel or the pipe wall or something. But it is required to be in the fluid. We're not allowed to take it out of the fluid. That'd be cheating. And then we integrate this equation 25 over the volume V. So what does that mean? When you integrate that, that's just a differential equation, right? Number 25 there. How do you integrate that over a volume? Well, you take your volume V, you cut it up into a large number of little volumes, for example, little cubes, each of volume dV. And then if these have a very small volume dV, then these quantities here in the integrand will be essentially constant. So you just and these terms here, by the way, of course, are the terms that we saw here in equation 25, right? That's the equation we're integrating. So then you multiply their value at that point in the volume V by the little dV, and that gives you a value, and then you add that up over all these volumes. And technically, you're taking the limit where dV goes to 0, so you have an infinite number of those things to add up, and so you call it an integral. An integral is like a continuous sum. So I do that for each of the terms in equation 25. You're allowed to just do it to the left-hand side and the right-hand side, and then break that into two separate integrals. It's because of the linearity property of this integral operation. And then I'm applying Gauss's theorem to two of the terms. And how did I pick out these two terms? Well, because those are the terms that have a partial xj here. See that? Partial xj from the advection and from the divergence of the stress tensor here. So when you, this is sort of going the other way in Gauss's theorem, but Gauss's theorem goes in both ways. When we have a partial xj in a volume integral, you can pass to the corresponding area integral by simply taking the thing in the numerator and multiplying it by the normal vector. Which component of the normal vector? The nj. The j has to be the same as the j there. And so here I have a sum over j because there are two indices j, and I still have the two indices j here. It's just now it's on an nj. A normal, n is a vector, n for normal, meaning perpendicular to the little surface a, or dA, and it's understood that there was an ambiguity in direction, right? It could have been pointing to the outside or the inside, and it points to the outside. And A is not just any old surface, it's the A that bounds the volume V. It's the boundary of V. And the other place in which I apply the Gauss's theorem is for this term here, and it's the same story. You replace the partial xj with an nj. And of course, there's a sum over j, and there should be an index. See, there's a free index I here in this term. That means we're talking about the ith component of the surface force, right? Well, there has to be a free index I here too. Otherwise, there's some sort of apples and oranges thing going on. I don't know if you've heard that expression, but it doesn't make sense. If here we have an ith component of a force, we'd better have an ith component of a force here and an ith component of a force here, or a thing that looks like a force. It's actually a momentum flux, but it's an ith component of a vector, which has the same units as the force here. Okay. Now, to get to Euler's equation, I want, so we're heading towards what's called Euler's theorem. It's a momentum balance applied to this integral over a volume of fluid. And but Euler was interested in inviscid fluid mechanics. So we consider the case where the flow is inviscid. So the viscosity equals 0. So the stress tensor has no off-diagonal terms. it only has the diagonal terms, but in the general case that diagonal stress tensor is the mechanical pressure, or minus P times, or minus mechanical pressure times the delta ij, just make sure that you're on the, or is non-zero on the diagonal, or it's 1 on the diagonal and 0 off the diagonal of the matrix. So Euler also considered the case of rho being constant and the body force is conservative. So in other words, you can write the force as the gradient of some potential, and I've written the potential psi here. So normally psi would be the gravitational potential. We're not going to write little MEC everywhere for the, to remind us that it's the mechanical pressure. It's the mechanical pressure that enters, and we'll just call it P. So we introduced those 3 restrictions in this balance that we derived quite generally for a steady flow. It was a very general fluid, but steady flow, no Eulerian time derivative. Now we introduce these 3 inviscid, homogeneous, conservative body force approximations, and we get the term simplify. So let's go one by one. Let's look at the body force integrated over the volume. Well, the body force was a gradient, because it's conservative, it's a gradient of a potential. But if it's the gradient of a potential now, and we're integrating over a volume, we can do that Gauss's theorem thing and replace the partial xi with an, and the whatever's up here in the numerator, psi times n. Which component of n? Well, it's the thing you took the derivative with respect to. So instead of xi, it's ni here. And it's an area integral here instead of the volume integral. And rho is just a constant, so I can bring it inside the integral here. It's like bringing it inside a sum of, an infinite sum. Okay, so that was the body force term. We had also the, remember there was the stress tensor term, but we replaced the, which we had already written as an area term, but now we're replacing it with just the mechanical pressure along the diagonal. That's all we did here. Well, I guess we summed over J, and then we just get the ith component of this, the normal to the surface. So even if your surface has a, say you're considering the x direction, if the surface is in the y direction, then this term does not contribute. But if the normal is along the x-axis, then this contributes completely. And if you're at some angle, if your surface is, you're interested in this force, but your surface is tilted at an angle, well, there'll be a cosine theta term here. Yeah, there's you have to take the geometry into account here when evaluating that integral. Okay, we'll see how that plays out in the applications. So there was a third term, but we'd already applied it as an area integral. So now we can just substitute this result and this result into our equation here. And so we have three area integrals in our equation that look like this. We brought them all to the left-hand side. And this result is known as the momentum theorem or Euler's theorem. It's a famous result in fluid mechanics. Euler was a Swiss mathematician who lived before Gauss. It was in the 17th century. It's from Basel, Switzerland. And did a lot of this fundamental work in mechanics and fluid mechanics. We can interpret this physically. So this flux of momentum through the surface A has to be balanced by the basically the potential energy term, if this is the gravitational potential energy, and the integral of the pressure along the surface. Yeah, and these are forces acting on the fluid on the interior of this surface by the fluid that's exterior, or at least in the case of the pressure, and in this rho psi term, it's not the fluid that's acting on it's the external gravitational field that's acting on the fluid at the boundary of this volume. And this term is the momentum flux. And I hope that's, well, maybe that's worth just a couple words explaining why this is a momentum flux. Let me let me cover up this. So I've got two U's there, right? U is the velocity. Let me just cover up one of them, and then we'll bring it back in later. So I have one. But if I do that, I can't point. Darn. So just imagine that UI is not there. Okay. I only have one mouse, so I can only can't cover it up. But then I would have rho, the mass per unit volume, times the velocity in the jth component of the velocity. And remember, we said that velocity, it has units of length per unit time, but it also has units of volume per unit area per unit time. So it's like a volume transport per unit area of surface that's it's fluxing across. And so it's a transport of volume per unit time per unit area. Which area? Well, this dA with normal in the direction nj. And so you might remember we looked at that in the last class, and we considered the case where the flow was across, so it was just flow in a pipe, but it was, we had a term like this, which was carrying fluid across a surface perpendicular to the direction of the flow. But then if the surface was tilted with respect to the flow, then it was just cosine theta times the velocity times the or that was the volume flux, was cosine theta times the velocity, and that's the volume flux per unit area of this surface that it's crossing. And what's theta? Theta is the angle between the normal to the area and the velocity. So if they're in the same direction, then the angle is 0 and the cosine is 1. And so that's a volume flux across this area. So it's volume per unit time per unit area. And if you multiply volume that by rho, which is mass per unit volume, then you get a mass flux across this surface per unit area per unit time. Okay, so without this UI, it would be a mass flux. But now I want to multiply it not just by rho, but by rho times UI. But UI is the velocity component in the I direction. So the velocity times mass is the momentum in the I direction. But it's not just mass, it's mass per unit volume, right? It's density. So it's the moment. So rho times UI is the momentum per unit volume of the flow in the I direction. So we're fluxing momentum density by the UJ velocity across the surface with normal in the direction UJ. So that's why I keep pointing to this term and calling it the momentum flux. It's balanced. This flux integrated over the whole area has to be balanced by these conservative forces and this pressure force. Okay, let's see how these we've just derived two important theorems in fluid mechanics: Bernoulli's equation and Euler's theorem, and they were energy and momentum equation balances respectively. And we'll see how they help us in practical situations. So we'll start with and then both of those are going to be useful in deriving this Betz's law, which I hope won't be I think I have just perfect amount of time. I have for 10 minutes on each. So we have, yeah, that's a good rule to keep me on track here. So let's use Euler's theorem, the one we just derived, to find the force on an array of rigid bodies inside a flow. It actually doesn't matter too much what these rigid bodies are. You could imagine a wire mesh that's used to like filter something. Yeah, it could be like a filter or some kind of grating. And I've well, we can read the text here, but then quickly we're going to look at the diagram. Otherwise, I find it doesn't make much sense. So let's consider an incompressible flow that's steady and uniform, or uniform velocity, U, capital U, far upstream, and it's impinging on some sort of array or say a wire mesh that's normal to the velocity, and the flow is bounded by some walls. Could be in a pipe or a channel or a canal, for instance. It could be like a river where we have a dam ditch and then put a pipe with some kind of mesh to catch the large things floating in the water. And then so you can, and our goal is to find the force exerted on this array or this wire mesh per unit area. And we want to use only fluid properties measured far upstream and those measured downstream. So let me show you the diagram here. So here's our flow field far upstream. And as you see, it's a uniform flow. So the velocity is doesn't vary in the cross-sectional direction. And just to give it a coordinate system, I said it's moving along the flow is along the x-axis here. So the y-axis is perpendicular to the flow. There's a z-axis, I guess, pointing towards us away from the screen, which we won't need. And then far downstream, we have the same uniform flow. And the cross section of this pipe, this could be a pipe or a channel or canal, is the same area, delta A here, as it is upstream. And it's a constant density. So by mass conservation, then if the flow velocity is u here, it has to be u down there, downstream. Otherwise, we'd be building up mass here in the interior or losing mass. So the mass flux here is the same as the mass flux there. So the u is the same as u, and the delta A is the same as the delta A. But the pressure downstream, P down for downstream, could be and will be lower than the pressure upstream. And in between, as I said, there's some kind of filter or wire mesh here, whatever I called it, the gray array of rigid bodies that I've shown just as black circles here. And but they're surrounded by a little dotted line, a little broken line, which is the control volume that surrounds the wire mesh, and we'll use that in the analysis, and we'll call that, we have to give it a name, so we'll call it A1 for this surface. A1 is the ensemble of all these little circular or cylindrical, if we consider the third dimension, the z direction. So there's cylindrical control volumes, and there's many of them, and A1 is the ensemble of all those surrounding they're in the fluid but close to this this wire mesh. And then A2 is the boundary. It could correspond to, well, this part of it could correspond to the wall of the pipe. This could be the wall of the pipe, and then this is the open part of the control volume, which is perpendicular perpendicular to the flow velocity. Okay, so I think that's described the experimental situation. Oh, just one sort of motivating comment here. Like, So this flow is going over this grating, and you can imagine there would be turbulent eddies here, and this would be a highly chaotic turbulent flow. And if you were to measure, you could stick a probe in there and measure what the flow properties, the velocity and the pressure, but you would find very chaotic turbulent quantities. But you can imagine if you go far downstream, it could be the velocity will settle down and become laminar again, and you'll have a steady flow with a easily measurable quantities downstream. Okay, so we want to do our measurements far upstream, far downstream. I've given you the values here, and then determine from that the force exerted on the wire mesh, you know, from these measurements. And so we apply Euler's theorem, which was equation 29, because even though it's turbulent here, it's a laminar to steady flow near the control volume boundary. We're going to assume that gravity is not important in this problem. So we have a narrow pipe, for instance, or if this is a channel, it's a narrow, or a shallow channel, or without any changes in height. I think I said this already, but the velocity is the same upstream and downstream. But that has an important implication. It means that remember in that Euler's theorem, there were three terms. There was the momentum flux term, the potential energy term, and then the pressure term, all acting at the boundary. Well, the momentum flux term is zero, or it integrates to zero. Why is that? Well, there's only two places where this is, when we do this integral, where this term is non-zero. It's when this velocity uj is perpendicular to nj. So the flow is across the boundary. Here we have a momentum flux into the domain. And here we have a momentum flux out of the domain. The domain is just the control volume indicated by this dotted line. See, across this boundary here is part of the boundary, the part of that A that we're integrating along. But this is all zero here because the flow is along the boundary. It's not across the boundary. But here we have a positive term because there's this flow in the direction of the outward normal. But here we have an equal and opposite term because the velocity is flowing parallel to the same normal, but the normal's in the negative x direction. So you get a minus sign here. So this momentum flux exactly cancels this momentum flux, and it's zero along the other boundary. So this integrates to zero. And we've said we can ignore gravity. So we got rid of gravity. We just got rid of momentum flux. We're left only with pressure. There were only three terms. We're down to one. So the integral over the surface of this control volume of the pressure times the normal unit vector is equal to zero. Okay, well, there's actually, so that's our simple equation. There's actually three components to this equation, right? Because we can choose I to be in the Y direction, the Z direction, but the interesting one is in the I direction, or sorry, I equals 1 or the X direction, because that's the direction of the flow. And then on the surface A2, now I've forgotten which is 2 and which is, yeah, so this is 2 and that's 1. Okay. So on the surface A2, the cross-section norm of the flow contributes delta A in the upstream. In the upstream direction, as I said, the normal is in the minus X direction. All right, so I've written that as minus I vector here. And the pressure at that point on the surface was P up for downstream, up for upstream, right? P up here, we're talking about this part of the surface. So that's minus unit vector in the X direction, P upstream times delta A. So that's, I'm just breaking this integral into the parts that are non-zero. So this is one non-zero part across that surface, the upstream surface. Downstream, the normal is pointing outward in the X direction. So this is the I vector, unit vector in the X direction. The pressure there is down, P down, and it's the same area, delta A. But now there's some, we could also integrate this integral over these control surfaces here that are on the interior. And there would be some pressure there, but we don't know what it is. But whatever it is, it leads to the force on this array, on this wire mesh thing. But that's the thing we wanted to know. So we're just going to, even though we, well, that's the unknown in this equation. And so let's just write that as F array, the force on the array, the total force, and then we're going to divide it by the area later to get the force per unit area, I think. And then, so let's put the things we do know or can measure on the right-hand side. So then these minus P up becomes plus P up, minus P down times delta A. That allows us to make measurements far upstream and downstream only of the pressure, and that'll give us the force on the array per unit area. That's at least in the X direction, in the direction of the flow. So that's a nice application of Euler's theorem in a only slightly artificial, well, it's not a, it's a restricted example, but a real world sort of example. And in fact, we're going to use that in the next, or we're going to use that in a minute. I think I have to, I think I'm not going at my correct speed, right? I took 5 minutes too long, so now I have to. No, because yeah, no, I'm okay, because I thought I had to go through Bernoulli's equation separately, but it's actually within this thing, so I should be okay. Yeah, let's Now we're going to use, now we're going to derive Betz's law, which is a law that expresses the amount of power you can extract from a wind turbine. But this is an upper limit. So we're going to make idealizations that allow us to extract the maximum amount of energy. And that will be like an ideal case. I guess I've read that in real world applications, one can approach about 75 to 80% of this ideal limit. So you can get about 80% of, or up to 80% of Betz's limit. So it's a useful idealization, but in reality, you tend to get less than that. Not surprisingly, because we're going to see that we assume that the flow is inviscid, so we have no frictional losses. We assume we have an ideal turbine, etc. You'll see as we go through it. So it's a maximum theoretical power that can be extracted from, for instance, a wind turbine. It didn't have to be a wind turbine. It could be a turbine in the ocean. It could be in any fluid, any situation where you have a fluid flow and you're trying to extract energy from it using a turbine. We assume it's largely to simplify the analysis, but also to make it the ideal situation, the maximum yield. We assume it's a homogeneous, incompressible, frictionless fluid in a steady flow. So steady flow simplifies the analysis. Friction makes it the ideal limit. And incompressible, as we've seen, is a very good approximation in the atmosphere and the ocean. And homogeneous says the density is constant. It's actually a reasonable approximation as well, but also simplifies the analysis. So for the turbine, we assume that it has an infinite number of blades. We're going to call it the disk actuator, but it's just sort of imagine a wind turbine. And the thrust is uniform over the disk, and there's a non-rotating wake. So you can imagine that often in real world situations, when the wind flows over some turbine, some of the energy is lost because energy goes into rotational motion of the flow downstream of the turbine. So we're going to ignore that, or we're going to idealize the situation by imagining we can consider the case where you can reduce that to zero. Again, it's to get the upper limit here. That's our strategy or our goal. So we take a control surface, which is a stream tube shown in figure 2. So here's our situation. We have an upstream flow. I'll get to this in a second, but we have an ambient pressure, like one atmosphere upstream. And, well, it doesn't have to be, but just some ambient pressure, for example, the 1 atmosphere. And if it's in the atmosphere, and then we have some upstream, uniform upstream velocity and some area upstream, but the upstream area is the area here of the boundary of our control. Here's our control volume. And so it has an upstream sort of entrance of area delta A up for upstream, which is this area here. But then it's bounded, it also has another part of the boundary, which is formed by the stream tube. Remember, we learned the stream tube was the surface created by the stream lines. And which an ensemble of streamlines. What streamlines? Well, they were the streamlines that passed through a set of X starts, starting points that form a closed loop. So we're imagining a loop here. I guess you'd have to turn it into the page here to see the loop, or you don't see, you see the loop as a line, right? Because of our perspective on it. And but it's a closed loop, and there's a set of streamlines running through that loop that form a surface that's a control volume, or forms part of the control volume boundary, and that's the stream tube. And remember that this is a steady flow, so the stream lines actually correspond to path lines, which so particles travel along this line here. Some of the air will, some air molecule will, some bit of fluid will travel along this line here, but the rest of it will travel through the interior, or some will travel through the interior. And then we have another boundary on this control volume, which is the downstream open end here, where the fluid flows out of the control volume. It exits into the ambient pressure at a speed u down, which is not necessarily the same as u up. In fact, it'll be less. But then to have conservation of mass, you'd have to have delta A down, this area down, shown by this line here, has to be bigger than the upstream inlet. I guess you'd call this the inlet, and this is the outlet. So the outlet has to be bigger than the inlet because it's moving more slowly. Maybe we can just pause and say, like, or pause, or not pause the class, but consider for a second, like, what's going on here? Like, we want to extract the most. Let's just use our intuition here for a second. We want to extract energy from this flow, right? So we want to have a turbine there that interacts with the flow. So we want the flow to slow down, because the more energy lost, more kinetic energy lost from that flow means more energy transferred to our turbine spinning it, right? So we want the most. But then if it slows down too much, it kind of builds up there at the outlet, and we can't get rid of it. So there's some sort of compromise going on there. You want it to slow down a lot, but not too much, because you want it to get out of the way so that more can come in after. So that's going to be our goal, is to find the sort of the ideal compromise here. And yes, and this Euler's theorem and Bernoulli's theorem actually help us a lot in coming up with that. So I think we're ready to consider actually, maybe I'd better read my notes before I try and guess how I did it. Yeah. Okay. So we start with we want our strategy is going to be to find two expressions for the x component, x being along the axis here, of the force per unit area on the actuator or the turbine, if you like. So it's actually a lot like the grating problem that we just did, or the wire mesh, except that it's now we have a momentum flux to consider, because the velocity is higher upstream than downstream, and the area is smaller upstream than it is downstream. So it's a bit like the wire mesh problem, but more complicated. So we can use our Euler theorem, equation 29, and I'm sorry. So actually, we can do exactly that analysis that we just did on the wire mesh, but we have to be careful which control volume we apply it to. We can imagine a new control volume embedded in the old one, which is this control volume here. Can you see that? There's a dashed line. The solid black line is sort of my turbine, the actuator disc or turbine. These are the turbine blades that are in this ideal representation are infinitely thin. So I drew them as a vertical line here. They're spinning around. And but then just upstream, I have a control surface, and then just downstream of that infinitely thin turbine blade, I have another part of the control surface. So I'm considering a new control surface just around the turbine. But see then so why did I do that? Because then it's not strictly true that the area downstream here, I shouldn't call it downstream because it is downstream, but just after the actuator, I'm going to call that area here delta A actuator. Actuator is just another word for the turbine. And then delta A upstream, just upstream of the actuator, is delta A. It's essentially the same A here. It might be a tiny bit smaller, but in the limit of an infinitely thin turbine, this A would approach that area. So then the velocity upstream, just upstream, let's call it UA, of this actuator has to be, by conservation of mass, has to be the same as the velocity just after the turbine. So now we have exactly the same situation with wire mesh, and we can say that the force per unit area on the turbine is like on that wire mesh. It's just the P before minus P after, just before the actuator and just after. So I do that integral, it all just collapses down to this. Okay, so I need to know this P before and P after. How am I going to get the P before and P after? Now I use, oh zoot, I'm really running out of time. Okay, well, if you're willing to, if you have to leave, that's okay, but I'll continue here for those who can stay, and then we'll have a recording of it, and because it's very important that I finish this. So we need to know that pressure just before, right? And so we use Bernoulli's theorem. And Bernoulli's theorem says that the kinetic energy density plus the pressure plus the gravitational potential energy, but we're ignoring the gravitational potential energy, so we just have these two terms, has to equal a constant along the streamlines. And so it's streamlines that connect, there's one streamline, but there's a whole series of streamlines passing from here to just before the actuator. So I can apply Bernoulli's theorem or Bernoulli's formula well, for saying that those terms are constant along a streamline. And so I know their value here. I can relate their values here to here. In other words, I only have to know the difference in velocity there. For instance, the upstream velocity and the downstream velocity, or this velocity at the actuator tells me the pressure, the relation of this pressure before the actuator to the pressure, the ambient pressure. And I have a similar expression here, which is Bernoulli's theorem applied for a streamline that's passing from this just downstream of the actuator, so from P after to P ambient, and connecting this, again, this U actuator to the U downstream. So I applied that Bernoulli's theorem twice. I take the difference between these two Bernoulli theorems. Why do I do that? Well, this term will cancel that term. This term cancels that term. And so then I just have this difference in the kinetic energy density between the flow far upstream and far downstream equals the difference in pressure far upstream and just before the actuator and just after the actuator, because far upstream and downstream, it's the same, it's the ambient. So that's useful, right? I can just, that's the pressure difference that I wanted to get my force here per unit area on the actuator. So it's just related to this kinetic energy density far upstream and far downstream. Okay, that gives me my force, but the problem is I don't know the far downstream velocity, and furthermore, I don't know how to optimize this thing. Remember, the whole goal was to optimize this thing, to sort of choose the arrangement such that the downstream velocity was the ideal compromise, giving me the maximum force per unit area. It's actually the force, we want the force times the velocity, right? Because that's going to give us the power rate. Well, we'll get to that in a second. Okay, so first I want to resolve this ambiguity by getting a second expression for exactly the same quantity here. And I do that by applying this momentum equation and the apply to a control surface with this stream tube. Yeah, sorry, this is the one I started to apply it to at the start. I want to apply it to the control surface made up of this stream tube and the two open ends far upstream and downstream. When I do that, I have the momentum flux far upstream plus the difference in pressure across the actuator This is just looking at the x component, right, of that integral. And then I have the momentum flux out of the domain at the far downstream outlet, what I was calling the outlet. And then so that's the main expression, which comes again from that Euler theorem applied to this big control volume. Maybe I'll just outline this because I did this before, but then I didn't apply it. So this is the big control volume that we just applied that Euler theorem to. And first we applied it to the little control volume there, but now we apply it to the big control volume. And then to sort of manipulate this, it's convenient to recognize that the density times the upstream velocity times the area of this inlet upstream, that's the mass flux, right? As I've argued a few times, this is a volume flux per unit area times the area times the mass per unit volume. That gives you a mass flux. So it has units of mass per unit time fluxing into our system. Well, mass is not created or destroyed here. There's no sink, so that has to equal the rate at which mass is leaving the system. So let's just call it m dot. So this is the mass flowing out at the downstream end, the outlet. And then, bearing that in mind, we can write this terms like this as just take out one of these u's here, and then you have rho u up delta a up, which is m dot, times that u up, which we took out, right? So what happens here? We take this is p before minus p after times the delta a. We've just recognized that nx is a unit vector in the x direction, so we're only considering the x direction component. And then we've moved the other terms to the right-hand side so that we should have there's a minus in front of the u up squared term. But this u up squared term is really just u up times m dot. And this other one is, I realize some of this algebra is a little bit hard to follow, but it's all there. And if you sort of work it out, you'll find, I'm just doing algebra at this point. So it's m dot times the difference in velocities far upstream and downstream. And then, and then you can apply this m dot with the flow velocity anywhere, right? It could be the flow at the actuator, but you have to use the right area. You have to use the area at the actuator. So the density times the area of the actuator times the velocity at the actuator equals the mass flux m dot times this difference in far upstream velocity and far downstream velocity. And so that too equals the force per unit area on the actuator. So now we have two expressions for the force on the actuator. One involving the squares of the velocities, and one involving the actuator velocity and the up and downstream velocities. Okay, so we're going to set those equation 42 equal to equation 39 because they're both two expressions for the same thing. And then you should go through this again at home, but this is my and work through this step by step. But you'll see when you set these two equal, you have something squared here. So some of these hints that I'll give you now are useful. Like you can write the difference of these two square terms is that one minus that one times that one plus that one, right? Because the cross terms are going to cancel. But then that's useful because I have u up minus u down, and I have a u up minus u down here. So I can cancel that and cancel that. And so I'm just left with u actuator velocity equals 1/2 the sum of the upstream and downstream velocities. That's kind of a remarkable result, right? It's like, this is just, it didn't have to be this simple, but it is. The velocity at the actuator is actually just the linear average of this upstream and downstream velocity. Amazing. So I guess this UA has a name, the axial induction velocity. Or I'm sorry, the axial induction factor, A, is the fractional decrease in the wind velocity between the free stream U up and the rotor blade here, the actuator velocity UA. So we take U up minus UA and normalize it by U up, and that gives you A. And then we just manipulate this thing. So that we have UA written, U actuator written as U up times this factor involving the axial induction factor. And then we can write the downstream velocity in terms of this U up times 1 minus 2A, and then we require A less than 1/2. If A here were bigger than, well, say A equals 1/2, then you have 1 minus 1. So you have 0. Sorry. Then we have 0 as our downstream outlet velocity. So then we would have run into that problem that we wouldn't be getting rid of mass from the output of the turbine. So that wouldn't work, right? So A has to be less than 1/2. But we'll see it that it is. We want to maximize the power output. Yeah, so here's where we consider the power. So the power, remember, is the force times the velocity. It's the rate at which you're doing work. So it's force times distance divided by time. So the distance divided by time here is the velocity of the flow at the actuator. So that's the force that we just calculated per unit area times the velocity at the actuator, which is using the first expression we derived, which involved the velocity squared. Right, that's the force. That's the force involving the velocity squared times the actuator velocity to get the power. And then we use these expressions we derived earlier relating the downstream to the upstream And the UA to the upstream velocity. So we get one U up from that along with a factor like that coming from there. And then a U up squared here gives us a U up cubed times 1. And if you work out, I'm skipping over the details of the algebra involving the A here, but if you combine all those factors of 1 minus 2a for squared here, and you work out that comes up to this term in A. That is all just to get the power in terms of these parameters. Now we've expressed the power. This is the key thing. We've expressed the power in terms of parameters like the density, which is a constant, the area of the actuator, which was a constant, and the upstream velocity, which is some sort of input to the problem, right? And then this A parameter, which is something that we can imagine that we can adjust by, tuning our turbine system. And so the question then becomes, what's the best value of A such that we maximize the power? Well, this is a polynomial, actually, in terms of it's a very nice mathematical expression. It's just the power is a polynomial in A times these parameters. So in calculus, we learn to optimize these things by finding the maximum and the minimum by differentiating them with respect to the thing we're allowed to vary, and the thing, or we can imagine varying. So we can vary this A. So let's differentiate the power with respect to A and set that derivative equal to 0. That'll give us either a maximum or a minimum. We have to go back and check after whether it's a maximum or a minimum. I'm sorry, I don't want to go through all the steps here. I just want you to get all the details of the steps. I just want to tell you what the steps are. So you set that equal to 0, you do a bunch of algebra, and you get that this has to equal to 0. These constants are not 0, so this thing in square brackets has to be 0, and it will be when A is 1/3. Which again, it didn't have to be such a nice fraction, but so A is 1/3. And well, there you have it. That's how you get the maximum power. And we can define, I guess, Betz's coefficient, which is, we're going to take this power and just normalize it by a power that appears in the flow. So let's look at the power available in the wind. The power available in, well, I have to be careful with the word available because there's not 100% efficiency. The power that the wind has, okay, let's put it that way. The wind has a power, just the power associated with the flow is 1/2 the mass per unit volumes times the area times the velocity cubed. So this is the kinetic energy flux of the or kinetic energy per unit volume flux in the wind. So that's the source of our power, is the kinetic energy flux in the wind, and we're extracting that power using our turbine, which we've imagined is, frictionless and ideal, and we've chosen our A parameter. We've tuned our system so that it gives us exactly the ideal A of 1/3. So here I wrote it A in general, but it's 1/3 for the maximum. Sorry, let me back up. So this is the kinetic energy flux in the wind, and then we're extracting, which is our source of power, right? And we're extracting this power P from it with our turbine. So the ratio of the two is going to be something less than 1, right? Because we can't get more power than there's in the wind. The maximum power we can get is when A is 1/3, and that turns out to be 16/27. Again, it's a bit amazing that it's such a nice fraction. That turns out to be, about 0.59, so a bit less than 60%. So that's Betz's limit, that's Betz's coefficient, actually, the power coefficient. So it's what it represents is the fraction of power that's in the wind that you can extract with your turbine under these very ideal situations of a frictionless flow and an infinitely thin turbine blade, etc., and no rotational loss in the wake. And so as I say, you don't achieve that in practice, but it's nice to have this theoretical limit. Yeah, so sorry for going way over time, but I wanted to